Hey everybody, welcome back to Adventures in Machine Learning. I'm one of your co-hosts, Ben Wilson, joined by
Michael Burke. Hi everyone.
And this week, we're going to talk about a topic that we've talked in private outside of recording a number of times, and about how important it is, EDA, Exploratory Data Analysis. And we're going to just sort of riff on what we think is important about this topic, things that we've seen, things that we've done, how we've been burned in the past, and just have a general stream of consciousness discussion about this. Sound good?
Sounds great.
Hey folks, this is Charles Max Wood from Top End Devs, and lately I've been working on actually building out Top End Devs. If you're interested, you can go to topenddevs.com/podcast, and you can actually hear a little bit more about my story, about why I'm doing what I'm doing with Top End Devs, why I changed it from devchat.tv to Top End Devs. But what I really want to get into is that I have decided that I'm going to build the platform that I always wished I had with devchat.tv, and I renamed it to Top End Devs because I want to give you the resources that are going to help you to build the career that you want, right? So whether you want to be an influencer in tech, whether you want to go and just max out your salary and then go live a lifestyle with your family, your friends, or just traveling the world or whatever, I want to give you the resources that are going to help you do that. We're going to have career and leadership resources in there, and we're going to be giving you content on a regular basis to help you level up and max out your career. So go check it out at topenddevs.com. If you sign up before my birthday, that's December 14th. If you sign up before my birthday, you can get 50% off the lifetime of your subscription. Once again, that's topenddevs.com.
Yeah, I was actually really excited for this episode. Last week, we decided we were going to do some EDA talk. And so this week, I looked up some tips and tricks online for what EDA is. And I'm going to read one set of tips to you guys. Let me just pull it up. So the first step is read in the data and import your libraries. Very important. Second step is look for missing values. Third step is visualize those missing values. Fourth step is look for positive correlation. Fifth step is look for negative correlation. And then you're done. So that's how you do EDA. End of episode.
I mean, I would add a few more steps in there, but I thought step one is funny. I mean, reading in your data, that's kind of pretty critical wherever you're going to be looking at it. But what do you think about data size and what sort of environment you'd be loading in data to do EDA?
Yeah. So to be perfectly clear, I think that list is terrible. I think reading there are a lot of like good points in there, but it's so subject specific. It matters a lot what your end use case is, matters what data you're doing. It matters if you have subject matter knowledge about that data. But going back to your question, Ben, about data size, often if you're working with large data sets, you just can't really do EDA effectively. If it takes an hour to run a histogram, well, you just can't iterate. You can't learn about the data fast. So it's really important to downsample. And do you have thoughts on how to approach downsampling? Is just a random sample over features, over every feature, for instance, good? You usually narrow down the feature set before you downsample and then look at graphs. What's your approach?
Ooh, it really depends on what the use case is and really where I'm running it. So, and also what the actual modeling type is. So if we're talking about something like classification, we have two major families there. Are we talking about a binary classifier? Are we talking about a multi-class classifier when we're talking about traditional ML? And if it's binary, the easiest, quickest thing that you can do on your featured data set, look at your labeled data and say, what is my general split between these two? And I consider that part of EDA. I don't know if everybody does, but understanding that is going to inform all of your following stages of that project. So if you have a 50-50 split on your data set, you can kind of get away with not worrying too much about any additional processing steps or any sort of fancy sampling that you need to do in order to create, train, test, and hold out. You can just basically say, random samples. It's going to be fine. You can, if you need to downsample to do a visualization, which you will if you're dealing with massive data. If you have a pretty even distribution, you're good to go. But if you have a 1 to 1 million ratio, you're talking about fraud detection, churn detection on a business that has a really sticky baseline of customer support for your product, or you're trying to classify aberrant behavior that just doesn't normally happen very much, you're going to have a massive skew. So it's important to understand what that skew is up front. That's usually the first thing that I'm doing if I'm doing a classifier, is just look at what the distribution is of the labels, whether it's binary or multi-class. And I'll annotate that, and I'll maintain a log while I'm working on the project. I'll create like a little dashboard of notes. It's like, hey, here's the problem that I'm working on. Here's how to get the ground truth, the source of truth for my labels. And if it's a classifier, I'm reporting out what that distribution is.
Yeah, that's a really good point. Because if you have a bunch of outliers at the top and you downsample, you might be throwing them out, for better or for worse. But I think it'd be helpful to take a bit of a step back. And so let's say we're doing EDA for machine learning. We're looking to develop a production model, whatever that means, we're going to be doing it. What would you say the purpose of EDA is in that setting? What is you come in with a feature set and just a data set. What is the output of EDA?
I mean, hopefully a filtered data set. It's something where what I use it for is to understand. When we're creating a feature set, that's a hypothesis that we're testing. And it's usually your first iteration is, I think that this data explains this label well enough that I could train a model that could attempt to estimate the correlation here, not the causation, but the correlation. And that hypothesis needs to be tested. But before you can test that hypothesis, and the way that you test that hypothesis is by training a model and then validating it on holdout data. But before you can test that, you have to make sure that the data is able to be trained. So yeah, one of the things that in that comically short list that you found, check for nulls. Yeah, that's a pretty good one. I usually do a blank filter, like a very dumb filter on my target for supervised learning tasks. So if I'm missing my ground truth, if my label is null, it's pretty hard to train on that. So all of those rows of data just get thrown out. And I've seen people do what they think is a not so risky thing. And I guess it depends on the use case, where they're like, well, if we don't have labeled data and we're missing labels, let's just impute them. Let's figure out what they potentially could be based on distribution of the features, or let's run an unsupervised learning model and see how close each of these vectors are in n-dimensional space to a known target. It's like, yeah, you can do stuff like that, I guess. That's kind of how something like Smoke works when you're imputing synthetic features, but you're polluting that signal with potentially unuseful or incorrect data. So it's risky. So I tend not to do it. I just throw out the data that's missing because I'm really just testing a hypothesis at that point. You can worry about data collection issues later and try to fix that if there's an ETL problem, or some backend system is not collecting that source of truth properly. But for testing out, as you said, like, hey, we're working on potentially something that could go to production. Just testing out that first few iterations, just drop that data. And then your feature data, it really depends on what it is that you're trying to do with regards to missing data in your features. When I'm doing an analysis, I want to know what is the ratio of missing to non-missing data. And if it's just a couple of rows out of many hundreds of thousands, then yeah, I could probably just drop it. It's not that big of a deal. But you want to analyze that and say, if I take this row of data that has this missing value in this one feature, is there a pattern that I can recognize here? So get a count of all of those, and then to just do a select where this feature is missing and visualize that. If it's a couple hundred rows, do some very simple plots of, hey, all the other features to the target. Run ANOVA and see, like, hey, is there some sort of common distribution here? And I'm dealing with the classification task and doing binary classifier. You would have in your x-axis of an ANOVA chart would be your label, a 0 versus a 1. And you would do an ANOVA plot for each of the features that aren't missing and say, hey, is there some pattern here where there's a clear difference between, some signal that's here that can let me know that there's a reason that this data is missing. It could be that it can't be collected when I have these conditions. And that could inform what you would need to do for imputation, or what would be a safe imputation. But if you run that at ANOVA and you don't see any signal there, there's no real difference between your class, your classes that you're trying to classify, or if you're doing a regression, you're basically running an X by Y plot of the other values to your target. And if you like fit a simple regressor, basically get an R square value there, and you're like, oh, there's really no relationship here, then you can safely drop that data. You're not losing a signal and imputing anything. You're not going to gain any signal there. So it's a waste of time and effort.
Being devil's advocate here, what if the relationship is highly nonlinear or needs some sort of transformation to then have a correlation with our Y variable?
You would run through those transformations as part of those other features. If you see there's some logarithmic relationship of each feature to the target, or something that just really stands out as saying, hey, this isn't something that we can do like a linear comparison to, then yeah, transform it. Get it so that you can do a linear approximation of relationships there. Although for the NOVA use case scenario, that should come out regardless of that association, whatever the distribution is, provided that the distribution is similar between those within those labels. And if the distribution is different, then that tells you something as well. Hey, wait a minute. There's an exponential relationship between this feature and this one class across these boundaries. What's going on here?
Yeah. Speaking of what's going on, I think a very common mistake that people make is they assume that the data are clean. They assume that it is exactly representative of what we would be seeing in production. And that often comes from an academic background. If you're fresh out of school, you haven't really seen lots of real world data sets where you have to clean, where you have to ask questions, where you have to understand that maybe there's a scheduled job that runs this so that the data comes in 5-minute increments instead of being continuous and things like that. So it's really important that when you're doing this initial step, you don't take stuff for granted and you actually go and question it. An example, like literally 2 days ago, I noticed that the distribution of one of my variables was exactly that. It was in increments of 1 minute, but every third minute, it would be a lot lower than the rest of the minutes. And I was like, well, what's going on? Are people doing stuff differently every third minute? And it turns out that just our analytics pipeline aggregated to the third minute for some events, just because that's how the back-end job was doing it. And prior to this, I was aggregating to a much larger level, so like to an hour or like a 30-minute chunk. But if you drop down to the minute level, I thought maybe more granularity would help my project. It turns out that there was some weird stuff going on. And so just to take that a little further, if you aggregate to, let's say, a 15-minute chunk or a 20-minute chunk, those 15-minute chunks and 20-minute chunks won't be even. And if I hadn't have plotted that variable, I would have never known, and it might have messed up my model. So just something to consider is that in the real world, data are usually generated by people, and then those people generate jobs that have schedules, and it's not always clean or representative of what we would see in production. So just something to consider.
I would argue on that point that it wouldn't probably have broken your model. That definitely would have broken your model. When you introduce a signal like that as a feature, it's like, hey, I'm looking at this temporal sense of something happening. If it's that clean of a signal, where you're like, hey, I have a value of 100, then 100, then 50, then 100, then 101, then 49. And it's this repeated pattern that's in there that like a model's going to learn that, air quote, learn, but it's going to find that correlation that's probably going to be much stronger than other things that you have in your model. And I couldn't agree more. It's super dangerous. And I want to iterate on your point of really understanding the data. I actually do that stage prior to doing stuff like NA filtering and looking at the data. If I'm building a data set for my first hypothesis, that's not me going into the data warehouse or on the Delta Lake or the data lake and just pulling data at random and being like, this seems like it's useful. But for me to even determine what data to attempt to build my first hypothesis, I'll go and talk to the data engineering team or the BI team and say, hey, what data do we have around this problem space? And I'll get a list of, or maybe I'll get ER diagrams if they're a really sophisticated, BI team, or if the data engineers have something that be like, oh, here's the query that populates this sort of data from raw to, our silver layer that you're going to be looking at. And then I'll take that list and I'll go to the business unit that probably asked for me to build this solution or help them out with this. And I'll ask them like, hey, what do you know about this data? Like this feature, what does that mean to our business? And I'm doing a sanity check at that phase because I'll ask the same thing to the BI team. Like, hey, this sales figure that I see here, how do we calculate that? And they may say, well, it's, cost of good acquisition minus depreciation. They may have this super complex formula that you then go talk to marketing and say, hey, how do you think this is calculated? Or what is this? And they may say, oh, that's the MSRP. Like that's the sales price of this thing. And then you go talk to finance, be like, hey, what is this data? And they may give you a completely different answer. And I'll do that with anything that isn't overtly obvious. If it's something like order data, well, just because there's an integer or an aggregated integer that's in that table of number of units sold in an hour, or in your case, for your industry, like number of minutes watched, is there a formula that is in place prior to that arriving in the location that you can see that you need to understand?
Yeah, I was about to bring it back to that as well. So the example is that Ben said, let's say we have 5,000 features and we're looking to do transformations on all of them and then visualize all of them. Obviously, you can't do that. And the single fastest way to reduce your feature set is to understand what features are and what features should be relevant to your label. And as Ben said, the most efficient way to do that is to just ask people if you don't have the subject matter knowledge. I haven't seen a successful project where someone goes in and does not learn what the data are telling them and does not learn what the subject matter are telling them, because it allows you to do EDA efficiently. It allows you to have instincts and intuition about where to look, what this should be doing, what this shouldn't be doing. And also, if you say, let's say this variable has a negative correlation when it should have a positive correlation according to subject matter knowledge, well, that's something that's very, very interesting. And it's either a data quality issue or it's something that's very relevant to your data set, maybe a problem, maybe not a problem. So knowing what exactly your data represent and what everything means is not an optional step. And a lot of people unfortunately think it is because coding is fun, but you really got to get into the data and understand what's going on.
And talk to other people.
Mm-hmm.
I couldn't be more in emphatic agreement with you about it's not just saving time, but it's saving frustration for you and the business later on. If you include something that is either A, completely irrelevant and not related to the problem that you're trying to solve, but it looked good, you can have correlation all day long, every day on things that have absolutely no relation to the problem that you're trying to solve because some latent factor happened to be influencing both of them at the same time independently, but doesn't mean that it's related. And then the other point that you brought up with like, hey, I'm changing my data, resolution for this row value of how I'm aggregating this. And then all of a sudden your distribution of data over time changes. If you don't like really go down and understand how that data is collected or what that data really is, slight modifications in production can have incredibly serious consequences that sometimes are really hard to detect until you're looking post hoc. Like, hey, the model's been running for 3 days. Why is our lift now negative? Like we were plus 8% lift on this and we were having this great outcome. We're making all this money. And there's some change last week in prod that we pushed the new model and now it's inverted. We're at a 15% loss. What's going on? You realize like, oh, well, the correlation was good when we retrained it, but in production, maybe the data is slightly different. Who knows?
Right. Yeah, we've beaten this topic to death on this podcast, but we're looking to generalize. We're not looking to optimize accuracy. So yes, causation is how you generalize. But Ben, I had a question for you, something that I've run into in the past that has been a challenge, which is, so step one is, let's say, read in the data. Step two is get subject matter knowledge to understand the data. How do you get interested in subject matter knowledge? Do you just love every topic for projects you're working on? Are you really interested in optimizing models and making the best model possible? So that's what motivates you. Like, what angle do you take to sometimes trick yourself into being interested in data that might not be super sexy?
I have a negative reinforcement personally. I hate revisiting something that I messed up. So the worst feeling that I have is because I'm terrible at multitasking. Like I think most people are. If you're working on something complex, you want to just be able to focus on that and work on it. The worst thing that can interrupt that flow of working on something new that you want to build right the right way is pager duty. When something breaks and if it's something that's trivial and you're like, okay, it's throwing this exception because we upgraded a package. All right, let's revert that package and let's go back to business as usual. Or hey, you have a test failure. Okay, let's fix that test. There's like a timeout or something. That's different from, hey, the model is degrading faster than we expected. Whatever you were working on before that alert that you got, or that tap on the shoulder that you got from the director of ML at the company, or the worst case scenario, complaints from consumers of your model. You're like, this sucks. What did you do to this? That investigation can be as simple as reverting to a previous version that didn't have problems, and then do a retrospective, figure out why it was broken, get some lessons learned. It can be that, which will derail your work for a couple hours, or it could be weeks long investigation of reverse engineering why this thing is so broken. So my motivation for learning that data is I also do kind of like to understand problems. I don't know. I'm a nerd. I really love solving something. I don't care if people think it's trivial. Like I built some stuff that I'm like, okay, I know this is a pretty trivial thing. It's not something that's really important for, humanity as a whole, but it's a cool problem to solve. And I get to work with people in the company that don't do data science work and don't really work with data at that level. And you get to know people, you get to, solve a problem with other people. It's an exciting feeling, but the more that you understand of that, the more, it protects you from getting burned later on. That's a big motivation for me.
Yeah, it sounds like we're very similar in that realm.
Hi, this is Charles Max Wood from Top End Devs, and lately I've been coaching some people on starting some podcasts and in some cases just taking their career to the next level. Whether you're beginner going to intermediate going to advanced, whether you're trying to get noticed in the community or go freelance, I've been helping these folks figure out how to get in front of people, how to build relationships, and how to build their careers and max out and just go to the next level. So if you're interested in talking to me and having me help you go to the next level, go to topenddevs.com/coaching. I will give you a 1-hour free session where we can figure out what you're trying to do, where you're trying to go, and figure out what the next steps are. And then from there, we can figure out how to get you to the place you want to go. So once again, that's topenddevs.com/coaching.
A little story. Back when I was in middle school / early high school, as most kids do, I would play Xbox on the weekends and listen to TED Talks. Super common. And there's one video that really stuck with me. It was by Eli, the computer guy. He had this he was like a computer consulting guy with his own repair shop in somewhere Texas. And he told me, or didn't tell me, he made this video about this story where he was in the military and his job was to repair hardware that was used by people in the field. And always there would be a new giant pile each day when he would get to his desk. And he was like, damn, how can I get through all this? So he would rush. He would get it done, go to bed. Next day, same pile. Next day, same pile. And then suddenly some of his things started coming back to his desk. And he was like, what? I already didn't have enough time. What the hell? And so his drill sergeant came in and just laid into him and basically was like, you have enough time to finish what's on your plate. And he was like, no. And he was like, well, then you definitely don't have enough time to finish it a second time. Mm-hmm. And that just stuck for me. Rework is the worst possible thing. And it's so frustrating. But I was wondering, Ben, if you had seen other people in your field or on your teams that are good at EDA and good at getting into the data for reasons other than hating doing things twice.
Oh, definitely. And it's really industry specific from what I've seen. An interesting thing with statisticians, mathematicians, and data scientists is a lot of people stick in industries throughout their career, not necessarily in a single company. That's pretty rare these days, but except for some industries. But I've worked with people in, say, aeronautical engineering companies or in semiconductor manufacturing. People tend to stay within those ecosystems for their duration of their entire career. Unless they don't like it or they want to try something else, then maybe they'll move out of that. But a lot of people will just bounce from one company to another every couple of years, or maybe they'll stay somewhere for a decade if they really love it. But I found that people in certain, what I would call like pure engineering focused companies that are not related to software engineering, but are more, hey, work at a factory building something. There's a lot of skin in the game for getting something wrong. So people operate from a desire and a need for as close to perfection as you can be. So if somebody's building a model in those industries, not only is it an incredibly lightweight model, usually, it might have tons of training data, but the columns that are involved in that feature set have been so thoroughly scrutinized and understood prior to even pulling the data for the first time. When you look up like, oh, what is this particular signal on this tool in this factory? Like, what does that mean? People are like, hey, go to this Confluence page and here's 17 pages of text that explain what that one feature is. This is how this data is collected. This is the network bus address on this tool that this comes from. And here's the link to the document of that tool, like the user guide. And here's the design docs for why we decided to put this tool in this location in this factory. Here's how close it is to a clean room vent hood. There's all this data that's there that explain the nature of how that data is collected and what the expectations are. So they're like hard coded. Hey, here's our upper limit. Here's our lower limit. If it goes beyond these values, we're going to alert. Here's who gets alerted, when it gets alerted. So the reason that you have that sort of scrutiny on data in those industries is because the products are super expensive. The factories are expensive. You're not dealing with direct consumers usually. You're making stuff for consumers or making stuff that other people use or that your company is selling, but it's ludicrous amounts of money. You screw something up, you're not talking about like, oh, we lost, 50,000 in sales over this week. It's more like you screw something up in a semiconductor fab, you could have a fab scrap event. They're like, hey, guess what? We lost $147 million this quarter because of this model. Shut it all off. And by the way, you're all fired. So there's like this position of fear that people have, justified. You really don't want to get anything wrong. So you take a lot of time and people will have that motivation. But then I've also worked with people in regulated industries. They have a different sort of motivation and a different sort of fear. It's fear of regulators, fear of government. They're like, hey, we can't get this wrong because we have to explain this to an auditor. So we can't add in just random junk into this model and hope for the best. Like, you really need to know what each data point is and when something doesn't look right, how to obfuscate PII data. There's a lot of considerations. And then in the Fed space, you've got a whole different set of issues that you got to deal with, which I can't really talk too much about, but suffice to say, a lot of people take that stuff extremely seriously because there's a lot on the line for a lot of those use cases. But as we were saying before we started recording, like about mid-market and commercial companies, which I've worked for a number of them, you currently work for one, you really see a broader spectrum of people's motivation. At least I have. You see some people that they just love solving problems. You see other people that just really love understanding everything that they do about stuff. And then you see cowboys as well, people who just don't care. They'll be like, hey, what data do we have in the data lake? Right. We got 3,000 features. Yeah, just throw it into XGBoost. We'll do a feature importance at the end, see what happens. We'll keep the top 10. It's like, what? Like, how do you know what that data is? It can get a bit ridiculous.
Oh, yeah. Yeah. The purpose of talking about this, I think, is hopefully for the listeners out there. Sometimes it's hard to get interested in whatever data you're working on. And there's a bunch of different angles you can take. So Ben and I both hate doing rework. We also like problem solving. If you're in an industry where you'll get fired if you mess up, that's pretty good motivation usually. But there's also a bunch of different angles. Like, I worked with a guy, as Ben said, who just really liked getting into the data. He was the analytics king, knew everything about analytics events and how they correspond to literally every downstream table. And that was just his thing, his bread and butter. Another guy really likes using the statistical tools. So he likes trying this new type of plot and see if that'll isolate this effect. So getting into, like, finding a way to motivate yourself to get into the data is super, super important. And often it's not just second nature for a lot of people because maybe you don't love some aspect of what you're doing. Maybe you do, and that's great. And then you can just skip this. But there's a bunch of different angles you can take. But so that, let's say we've covered a couple steps now. So read in the data, get into the data, and figure out some motivation for why to do that. Handle missing values. We talked about that a bit. I agree with Ben that you shouldn't impute in the EDA phase. What would you say would be step 2, or I guess 4, the following step?
I mean, the next thing that I do is I'm going to make sure that I'm not introducing something that a model is going to struggle with. And that was covered in that bullet list that you read off at the beginning. Steps 3 and 4, I guess they had it. Is there positive correlation? Is there negative correlation? That's kind of, both of those are sort of loaded terms, because I've seen people do that correlation analysis where they just look at the feature compared to the label. And they're like, well, if I have 99% positive correlation to this target from my regressor, it's going to be an awesome model. I'm like, no, what that actually means is you shouldn't be using ML to solve this problem. You already have the data. Just use that data and write a if-else statement. You're done. Move on to the next problem. Right? Like if you have something that's almost 100% positive correlation and you know that you have that well before you would need to make a prediction, just problem solved. The problem that you usually see in that correlation analysis where some people don't go as far as they should isn't in checking for correlation to the target. It's checking feature to feature, like pairwise comparisons, and saying, hey, if I have feature A and I have feature B, and A and B are both 100% correlated to one another, that's fine for a linear regressor. There's options for regressors that will, on linear models, that will de-weight one of those or remove one of them completely. It's not so fine for tree-based models, where it's going to have an equal opportunity to split at that conditional because it doesn't know which one is better. And it becomes the decision of where to split becomes predicated on your seed value for your random split of how it's actually doing that within the tree algorithm. So it's actually dangerous because if you get drift in different ways over time between those two values, if the tree is splitting in a way that it expected that correlation to be matched between these two features over time, you could have a very interesting way of drifting where it's really hard to diagnose what's going on. The other problem that you can have in a linear system is, what if things are almost 100% negatively correlated with one another? What do your coefficients become then? They cancel each other out, sort of? Like, how does the model adapt to that? Well, it's going to struggle. It's going to have to iterate longer, and you're going to lose the signal of each of those things. But the real nuanced stuff is where you have what you mentioned earlier, is what if it's a nonlinear relationship between two features? And how do you capture the effect of that? What if the combination of these two represents some sort of exponential relationship with one another and it's not very noisy at all? You plot not a line chart, but you plot a scatter plot and you see what looks like an actual line. Ruh-roh, something is really messed up in the data. Like, naturally collected data should not look like that unless you are capturing every aspect of that problem. Then yeah, you should see stuff that's pretty, there's not a lot of noise. There's not latent variables in that. But for the vast majority of problems that are out there in the data science world, you're collecting data, you're not going to have a full picture of everything that affects that problem state. And if you do, you shouldn't be using ML because you already have the answer. But if you don't have any noise between that, look into what those data points are. Like, what are those features actually collecting? Is one of them built from the other one? That's something you see in ETL quite a bit. If you're looking at just a data warehouse and you're looking at a ton of tables that you could use to solve this problem, if you don't know where the derivation is of some of these calculated columns, you could theoretically have label leakage, or you could have compounding calculations. Where it's like, I've seen personally at e-commerce companies, I've seen people try to build models where they're like, hey, we're trying to optimize for cost in like what our sales price should be for this good. And then you look at the feature data and you're like, hang on, like you have the sales price in there. Like it's not directly, the column doesn't say sales price, but you have all of the data in that feature that explains where a decision in prior times would have been made from. So you're leaking the label in this model, and it's not doing what you want it to do. Or you have like a compounding effect where you're looking at like fraud detection is such a common use case that in industry. And you look at a feature set and you see that there's data that is at different levels of aggregation that's all been applied to that same feature vector. You're like, okay, you have, number of orders in that shipped to this location in the last, 15 days. And then you have another column in there that's like cost of orders in the last 15 days. And then you have another feature that is something that is the combination of the both of those, like orders times cost of products. And you have multiple different effectively copies of the data in that. Well, what's the model going to choose? Or how is it going to optimize around that? It becomes problematic and challenging to get a model that's going to not overfit like crazy to a very limited subset of features that you don't want it to actually learn.
Yeah, 100%. So let me see if I can recap a couple of the things you said. One of the things is look for label leakage. If there's leakage, your fit will be crazy good and deceptively so. Another one is look for correlations. This can indicate whether features are valuable. And also if there's correlation between features, maybe there's redundant information and you can just throw one of those features out. What other visualizations or EDA tools are in your toolkit that you use for most projects? So you mentioned scatterplot, ANOVA, correlations, and then subject matter knowledge about leakage. What else?
One other thing that I do that's in my checkbox of things for data that I do kind of around that time of checking for correlations and after I've talked to people is I check with backend engineering, whoever is generating that data that's eventually going to be ingested by data engineering team. And I ask them, when is that data created? And that's important to know on if you're going to be doing, a prediction based on something. Is that data going to be available or does it change over time? Are we mutating that and, getting something that's out of time bounds to put back into that row or that event data that we don't actually know if that feature is going to be available in time for prediction, but just do a validation of all that stuff. Make sure that, we actually have the data that we need, which vast majority of the time, you're not going to see that in a data warehouse. Data warehouse its objective is to be as correct as it can be as of that moment and have as much data populated as possible. But in a serving system, you might not have that. Might not even be something that you collect or you collect it the next day, post hoc populated back into a data pipeline. So that's always important to know. But other things that I check for visualizations, I don't know, I'm a huge stats nerd. So I like to do, if I'm looking at a continuous variable, I always want to know for that feature, what is that distribution? So some tools that are useful for that is generating a probability distribution function or a probability mass function. In PDF PMF plots, based on whether you're dealing with ordinal data, categorical data, or continuous data, understanding what that distribution is can let you know if you have data correctness issues or sort of a complex relationship of data. If you plot out that data and look at it on a continuous feature, and you're like, hang on a second, why are there two peaks in this data? Why do I have bimodality in this? Should I be looking at something else that's related to this? Should I be going upstream of this calculated feature? Because it looks like they're combining two different things here. Or there's some other feature that would explain the division of these two modalities. Or maybe the data's trimodal. There could be some confounding factor in there that if you throw that into the model, it's going to look like random noise. Most models aren't going to be looking at what that distribution is and saying, oh, I'm definitely seeing this signal here. The model is just going to try to fit to the correlation as best it can. And if it's pretty challenging to fit to complex distribution types. In fact, it's exceptionally challenging to do that. You usually have to transform that. So I would mark that. I usually keep like a spreadsheet open when I'm doing all this stuff. And I'll have, a column of that column name and then rows within that spreadsheet that have all the things that I need to validate before saying, okay, this is good for inclusion. And here's the link to the visualization chart that I generated, or a Jupyter notebook. It's one of the things that I use Jupyter notebooks for, is for this purpose, just so I can analyze everything.
Yeah. That's a really good point on understanding distributions.
Hey, folks, if you love this podcast and would like to support the show, or if you wish you could listen without the sponsorship messages, then you're in luck. We're setting up new premium podcast feeds where you can get all of the episodes released after Christmas 2020 without the ads. Signing up will help us pay for editing and production, and you can go sign up at devchat.tv/premium.
As we were talking about before, if we have really large data sets, often plotting a histogram for each variable is pretty expensive. So if you can find good summary stats like skew, kurtosis, whatever your go-tos are, they can help effectively and efficiently help you understand what's going on in your data and what the features look like. Because if it's a uniform distribution versus a heavy right tail, heavy left tail, that might affect how you approach things. So completely agree. Another tool that I like using for visualizations, well, two. First, for correlations, the good old correlation heat map is super useful. It plots everything right there for you, and you can then make informed decisions about all your variables from a correlation perspective. Maybe you have to do a couple iterations as you remove variables, but it's still a really great tool. And then another one is a QQ plot. It essentially maps the percentile or quantiles of one distribution versus another. If it's a perfect linear relationship, then it'll be sort of a line up and to the right. But often there are changes to the relationships at either extreme of the distribution, so on the lower left or the upper right. And if there's changes in the middle as well, that's often very informative for showing where potential relationships diverge or converge. So those are two other examples of visualizations. But yeah, it's a lot of personal preference and how you like approaching data, but knowing your summary stats is super valuable.
Yeah, in some packages, I know like Pandas has a data frame summary that you can use that I've seen so many people use it. And sometimes I'm a jerk to people that I'm mentoring, and I'll just say, okay, you generated that. Now explain what all of those values that are generated are. Or, using a proprietary statistical analysis toolkit like JSL or SAS or something. You generate that summary plot of data, of this matrix of data. You say, all right, explain what all of these things are. A lot of times I don't remember what all of them are. You look at, the correlation relationship report that comes out from stats models, which is different than some of the higher level APIs that you have for other toolkit and packages. But when you look at those low level stats libraries, the important thing is to know where to go to look for what those things actually are. Have a set of links that you can refer to, a little dictionary. And if you're on a data science team, make sure all that stuff is documented so that when you have that standardized report, when you're working on a project in a team and people know that there's this template that you have to follow when you're doing the EDA step, it's like, hey, if this is a candidate feature set, here's the operations that we need to see in this document that's been generated. It doesn't have to be extremely exhaustive and something that's going to take forever to do, but it's just like, hey, we have 8 features that are candidates for this model. Let's look at these, skew and kurtosis values. Let's look at Pearson's correlation coefficient of all the pairwise combinations here. I want to see the QQ plot and all the statistics associated with that. And if you have that in a templatized form, people can refer to that and understand, like, oh, that's what that p-value is here. It's can I reject the null hypothesis that these two distributions are equivalent? And if you have a really low p-value, I can say, all right, I'm 99.9998% confident that these are not the same because I have a p-value of 0.00001. That's what that actually means when you're looking at those sorts of comparisons. But having that documented, something I've done in the past, screenshot something, draw a bunch of lines and arrows to it, and then have little text boxes that explain to other people on the team, like, hey, this is what this thing actually is. And these are the values that we're expecting on this. And if you see this number or this sort of range of numbers, either ask somebody or here's where you go to look up what this actually means and how to handle it.
Damn, I wish my team did that. That would be game changing. I could understand all of data science overnight.
Yeah, I learned all of that stuff actually while working at Samsung Austin Semiconductor, a team there, a bunch of really great people that have been working on the memory fab for a decade before I got there to work on the LSI side of system on a chip design. And these people in the memory side, they had all this just locked down, and I absorbed it all like a sponge. I was like, why do you guys generate these templates and stuff? And I was asking all these questions to that team, and they're like, well, this is how we got burned in the past. from doing this. And we were doing yield analysis, and we did a report that, showed a positive correlation between these things, but it turns out it was spurious. And this is how you can determine that. And here's the functionality you can use. And this is the test you want to check. And when we started phasing out the memory fab over there, I was very eager to let management know, hey, we need all of these people working on this team that we've created over here. Get them over. And it was a great experience, but it's a lot of work. You need a lot of people to dedicate time and energy to building that knowledge base. But what it gives your team is the ability to bring somebody in from the street who might not even be familiar with your industry. They just know statistics and math. They've done some data science work or ML engineering work. And if you have that knowledge base that's built, that's specific to your company and your sort of data and how you want to structure things to eliminate problems, they can just refer to that. And that's the part of their 90-day onboarding. Like, hey, read through all of this stuff. Let us know if you have questions. Here's a quiz you can take that validates that you grok all of this stuff, and they can be a contributing member in weeks rather than years.
Yeah. Documentation is the key to onboarding, as I've learned several times.
Yeah. It keeps you away from tribal knowledge.
Yeah.
Tribal knowledge is the death of a data science team, because you're going to have people that there's only going to be one or two people that really know how that implementation works when they leave, and they will leave. If they're building the most complex stuff and they're the most knowledgeable about something, somebody's going to offer them a better job, more money, a higher position, something. They're going to leave. And if that's all in their head, good luck.
Yeah. I've seen that happen personally. It's not fun. But we're almost at time, and I wanted to ask one more question. What is the most common or most detrimental EDA mistake you see for machine learning modeling?
Not doing it. Seriously.
That is the answer. Yeah.
I wouldn't even be able to make a Fermi estimation on the number of times I've seen that in industry. If somebody's asked for advice, they show me their code, and I see at the top, from table A, select star, from table B, select star, from table C, select star, join on primary key ID. And you look at that and you're like, where is the definition of what features are going to be included? And you get in response like, well, tables never change. I'm like, yeah, but do you need all of those features? How big is this table or this feature set going to be? You end up looking at it. Okay, there's 200 features in there. I sometimes ask people, I'm like, can you explain how just 10 of them work? What are they? What is this data? And if they can't, at 10 random ones that I select, I know that, hey, nobody did it. And then you look at why they asked for advice in the first place. It's because their model is falling apart in production, or they just can't get it to work. It's too expensive to train. Validation sucks. They can't figure out how to tune it. And the reason they can't do any of those things successfully is because they don't understand what that data is.
Cool. That's what I wanted to say too.
All right. So I think we've been talking for like 55 minutes or so, but this has been fun. We could probably even continue this conversation in another episode talking about, all right, after you do the filtering and stuff, what's the next phase? And maybe we should do that for our next panelist episode, talking about transitioning from EDA and doing all that validation. How do we start doing feature engineering work, feature selection, and what is that iterative process? Why does it suck so much? Because it takes forever to do it.
Yeah, it's the worst.
Yep. All right. So thanks everybody for tuning in, and hope you enjoy what we talked about. Hopefully you got something out of it.
Yeah. Thanks for tuning in. Be sure to come in next week. It'll be scintillating, I promise.
All right. Until then, take it easy, everybody.
Bye, everyone.
Bandwidth for this segment is provided by CacheFly, the world's fastest CDN. Deliver your content fast with CacheFly. Visit CACHEFLY.com to learn more.